Acephysics.org. Yes! Yes, yes, yes! Here's an outline on this presentation I'm going to give on DC circuits. DC stands for direct current. I'll discuss how current flows in a DC circuit. I'll discuss Ohm's law. I'll discuss series and parallel circuits, power in circuits. And then on the follow-up presentation, we'll cover DC circuit example problems and conceptual problems. On that video, I'll solve several common and fundamental DC circuit problems. This slide shows some schematic diagrams and common symbols used in circuits. Electronic circuits are a pivotal cornerstone of modern technology, playing a vital role in numerous applications. They are used to explain how power travels to your house, as well as how your house distributes power to your electronic devices, such as televisions, smartphones, refrigerators, and more. Additionally, circuits are used to engineer microprocessor chips, empowering the functionality of your computer. This is a series combination circuit, which we will go over the difference between series and parallel in upcoming slides. Here's a parallel combination circuit. The standard circuit element for the symbol for a resistor in a circuit schematic is this squiggly line. The symbol for a battery in a circuit schematic is this picture right here. The long side of the battery is the positive terminal. The short side is the negative terminal. Here's a switch, which is open and closed. Every battery has an EMF. An EMF stands for electromotive force. In all practical purposes, EMF is the same thing as voltage. So the battery's voltage and the battery's EMF are the same thing. I'd like to very briefly discuss batteries. Batteries store and release electricity stored in the form of chemical potential energy. They produce current via redox reaction. Inside this battery, there's chemical potential energy. That's these arrows here is what I'm designating as chemical potential energy, the cream-colored arrows. And that chemical potential energy causes a charge separation. So the positive terminal of the battery has a conglomeration of positive charges, and then there's a group of negative charges on the negative terminal of the battery. And of course, these positive charges want to go towards the negative charges, but they can't because there's chemical potential energy which is separating the charge and keeping that charge separation and that voltage on the battery. Batteries are composed of two electrical terminals, namely the cathode, the positive terminal, and the anode, the negative terminal, which are separated by an electrolyte. The voltage of a battery, aka EMF, remains constant because the battery continuously separates charge until the chemical potential energy matches the electrical potential energy due to charge separation. To increase the battery's voltage, we have two options. We could choose different materials for our electrodes, ones that will give the cell greater electrochemical potential, or we can stack several cells together. How does current flow in a circuit? When you connect a battery or close a switch, a non-uniform surface charge distribution forms on the wires. So in this case here, these are wires. This is a resistor. This is wires. There's no battery attached yet, but we can attach a battery, and that would be closing a switch. And now there's a battery attached. When the battery is attached, surface charges and the battery create an electric field inside of the wire. So the first thing that will happen is when you connect a battery, there's going to be a surface charge that forms. There's going to be a charge that forms all over this wire, and then there's going to be a conglomeration of positive charges on the top of the resistor and negative charges on the bottom of the resistor. And what this results in is there's a uniform electric field inside the wire as well as inside the resistor, and this electric field pushes current through your circuit. The electric field inside the wire is uniform. The field pushes the sea of electrons through the circuit. The electric field in the resistor is much stronger than the electric field in the wire. In fact, we typically ignore the electric field in the wire. Electrons are actually what move, but we treat the current as the motion of positive particles. This comes from history and Benjamin Franklin. So in fact, electrons move through the circuit like this, and they move from the negative terminal to the positive terminal of the battery. However, the way that we analyze the problem is we say that there's positive charge carriers, and those positive charge carriers move along the electric field, and they move through the wire like this. Here's a little animation which shows a non-uniform surface charge density on the surface of a wire. And you can see it's very positive here. It's less positive. It's a little bit negative, and then it's more negative. And if you set up a surface charge distribution like this, this will produce a constant electric field within the wire. This is something that is not terribly hard to derive, although it involves integral calculus. And I'll do this in an upcoming presentation. I'll go through the derivation of how this works. But for right now, it's what you should know is that there's a charge distribution on the wire, and that's going to produce an electric field within the wire. Here's a paper by Mueller. It's called A Semi-Quantitative Treatment of Surface Charges in DC Circuits. In this paper, Mueller employs Maxwell's equations and leverages the intrinsic properties of equipotential surfaces to construct a model of the electric field within a circuit. While the paper is fantastic, its level of detail exceeds the scope of this particular presentation. The paper explains why the electric field in the wire is small and points in the direction of current flow. Shows that the electric field in the resistor is large and also points in the direction of current flow. The quick arrangement of surface charges on the circuit elements generates the specific electric field configuration. You can see this is the electric field within the wire, and this is the electric field within the resistor, and the electric field in the resistor is much larger than the electric field in the wire. The red is positive charge, so on one side of the resistor is positive charge, and on the other side of the resistor is negative charge, and that produces this electric field. And this is discussed and treated in this paper. I plan to provide a comprehensive analysis of this paper in an upcoming video that I will share online. Stay tuned for a thought-provoking and engaging discussion. To ensure you don't miss out on upcoming content, remember to subscribe and enable notifications. acephysics.org. When you solve DC circuit problems, it's beneficial to simplify the picture. The surface charges adapt to ensure small electric field in the wire and a large electric field in the resistor. Delving into the intricate configuration of surface charges becomes cumbersome and does not help in standard DC circuit analysis. To illustrate this idea, imagine I were teaching you how to prepare chicken tenders. If I began the lesson with the process of hatching, housing, and feeding and cultivating a chicken for food, that would be excessive and time-consuming. While understanding meat cultivation may be valuable for a chef, it isn't essential or particularly helpful in creating a delectable chicken tender. So when you're dealing with DC circuits, the big picture. After the switches close and transients go away, this is a matter of milliseconds, DC circuit analysis commences. Surface charges form on the conductor such that large electric fields exist in the resistor and small electric fields exist in the wires. The electric field pushes charges everywhere, producing an equal current everywhere. The work done by the electric field in the wire is negligible because it is much smaller than the work done by the electric field in the resistor. The analogy of a mass in the form of a rolling ball at different heights is an effective way to think about DC circuit problems. This slide discusses a mechanical analogy of current flowing in a circuit that I find helpful when I'm thinking about these problems. If we imagine that there's a positive charge particle right here, it's inside the wire, so there's going to be a small force on it, and the particle is going to be moving through the wire with a small force, and it's going to go, and then once it gets to the resistor, there's going to be a big force on it all of a sudden. But the particle is not going to be moving quickly because the resistor also has a big resistance. So even though there's a big force forward, there's also going to be a big force backwards. And then the particle is going to continue moving. Once it gets into the wire, the force forward is going to become small again because the electric field is small within the wire. And then the particle gets to the positive terminal sits to the negative terminal of the battery, and the battery does work to bring the particle back up to the positive terminal. Now, you can think of this with a mechanical analogy. Imagine that there's a ball right here, and it's on a very slight incline. So the ball, gravity is going to act on the ball in the direction of its motion, but it's going to be a weak force of gravity because the incline it's not steep. It's a very shallow slope. So the ball will move slowly along the incline. At a later point, the ball is going to get to this location. And then now at this point here, the ball will get here. And once the ball is here, the force of gravity acting along the direction of motion of the ball is going to be larger because the slope is bigger. Although we have to imagine somehow that there's going to be a big resistance backwards at this point. Once the ball hits this location, gravity is bigger, but there's also going to be a bigger resistive force because the properties of the surface that it's on. And so the ball, we'll assume, is not going to move any quicker because Even though the force forward is big, there's also a big force backward. So the ball is still going to slowly move down this incline, and it's going to get to this location, and then it's going to come here, and all of a sudden the force of gravity on the ball is going to be small again in the direction of its motion, but it's still going to move the same speed because the resistance has decreased, and the ball will get here, which is equivalent to the negative terminal of the battery, and then what the battery will do is lift the ball up and bring it back to the top, and you're just going to get continuous current flowing. If there's a ball at this location, the force of gravity pushing it along the track will be small because the angle's small. For example, if you go skiing on a large slope, gravity will pull you quicker than if you go skiing on a small bunny hill. However, if the resistance of the large slope is much more than the resistance of the small slope, for example, there are more obstacles or it's more dense snow, then the skier on the large slope would not move quicker. When the charged particle moves through the wire, the electric field and resistance they feel is tiny. When the charged particle moves through a resistor, the electric field and resistance force they feel is large. The electric field is large and the resistance is large. Imagine you're asked to push a person slowly on a slip and slide with low friction. You'd not need to push hard to maintain a constant speed. Imagine when the slip and slide ended, the ground was covered in rocks and sandpaper. If you were given the objective to push the person at the same constant speed, you would need to work hard and push with a larger force, even though they would not be moving quicker. On a side note, the person who was being pushed would have a large pain in their buttocks region. Okay, before this lady drops the puck, imagine that there was another person to the right of her who dropped the puck in air, not along the board with these resistive pegs. So one puck is being dropped and it's hitting the pegs, and one puck is being dropped in air. Which one would hit the ground first? You see that this is getting slowed down by the pegs, and that's equivalent to resistance within the wire. And it's not going quickly. And once it gets to the bottom, it's moving slowly. That's a lot of resistance right there. Here's an analogy with two resistors. So you have all of these balls rolling through this circuit. This one is going to have a small force on it because it's a small slope, and it's going to start moving slowly in this direction until you get to, and it's not going to lose much energy as it goes from this point to this point, and the charged particles won't lose much energy as they move through the wire until they get to the resistor. Then you get to this location here, and it's not going to go quicker. There's going to be a bigger force on it, but there's going to be more resistance. So it's going to stay the same speed, but now it's going to lose a lot of energy over this distance because it's moved down a lot. Then again, in the wire, you don't lose any energy. And then almost all the rest of the energy is lost in the second resistor. There's a little bit of energy left over that's lost in the wire. And then some outside agent, the battery or a person, lifts up the balls, and they just continue flowing in this constant current like this. Now I'm going to discuss Ohm's law. In equation form, Ohm's law is V equals IR. V is voltage. Voltage, remember, is also EMF for E when you're dealing with a battery. I is current. The units of currents are amps. R is resistance, and the units of resistance are ohms. So Ohm's law is V equals IR. You could also write it as E equals IR, where E is EMF. A resistor is a circuit element that regulates current. For a constant resistance, current will be twice as much for twice the voltage. So here's a situation where there's a resistor and there's some voltage over the resistor. I've put 4 negative charges here and 4 positive charges here. These positive charges want to move across the resistor and get to the negative charges, and they're pushed by the other 3 positive charges and pulled by these 4 negative charges, and I'm calling this V1, and that would produce some current I1. Now, twice the voltage would mean that there'd be twice the charge on this side and twice the charge on this side. So here, this resistor would have twice, if it's the same resistor, now the resistor has twice the voltage over it, and there'd be twice the current, which would be moving through the resistor. And if you had 3 times the voltage, then there'd be 3 times the charge accumulated on both sides of the resistor, and the force would be 3 times as great. The energy would be more, and it'd be pushing the current through the resistor at a larger rate, and therefore you'd have a larger current. This would have the smallest current, assuming all the resistors are the same. This current would be twice as big, and this current would be 3 times as big. In DC circuit problems, you must know the difference between parallel and series circuit combinations. It's important in physics, not just in DC circuit problems, in many circuit problems with all different types of circuit elements. Here are 2 resistors in series. This slide is dedicated to resistors in series. Here's 2 resistors in series. This is the top of the first resistor and the bottom of the first resistor, and the top of the second resistor and the bottom of the second resistor. And so if you notice, the bottom of this resistor touches the top of the next resistor, and there's nothing in between. If there was a wire that came off here and went somewhere else, it wouldn't be series. But this is series because the top of one resistor touches the bottom of the other resistor, and there's nothing else in between them. It's just a wire. And that's the definition of resistors in series. You could have as many resistors in series as you want. It's not just 2. It could be 3, 4, 5, 10,000. You can have as many resistors in series as you design within your circuit. Whenever you have whenever you have resistors in series, you can write them as one equivalent resistor. So these 2 resistors in series are equal to one resistor with a different resistance value, and that resistance value, the equivalent REQ, the equivalent resistance is the sum of all of the resistors. So REQ in this case would be R1 plus R2. If you had more than 2 resistors, REQ would be all of those resistors added up. This is a derivation for why resistors in series add up in this way. You can look up this derivation if it's helpful for you to see that. When you're dealing with series circuit elements, currents across all series circuit elements are the same. This is something you must memorize. You should also understand it, but you absolutely must memorize it. On this slide, we have resistors in parallel. Resistors in parallel, here are 2 resistors in parallel. The top of one resistor touches the top of the next resistor. The bottom of that resistor touches the bottom of that resistor. And there can't be anything in between. If there was a wire which was coming out of here and going somewhere, if there's a wire here, these wouldn't be in parallel. These are only in parallel because the top is connected with one wire to the top of this one. The bottom is connected with one wire to the bottom of the second resistor, and there's nothing else involved. Voltage across parallel circuit elements is the same. Whatever voltage across this resistor is the same as the voltage across this resistor. You must memorize that and understand that as well. And whenever you have resistors in parallel, and it can be more than 2, you can write those resistors in parallel as one equivalent resistor. These 2 resistors, for example, in this case, these 2 resistors in parallel are equal to one resistor, REQ, where REQ or RE is equal to 1 over REQ is equal to the sum of 1 over RI, where RI is each one of the individual resistance values. I'm going to go over several problems on the next presentation. It's important to see problems. To prove this formula, we know that current is equal to I1 plus I2. Whatever current leaves the battery has to equal to the current through resistor 1 plus the current through resistor 2. Ohm's law says V equals IR. This can be rearranged to say I equals V over R. And so then current 1 is V over REQ. And I'm sorry, current total is V over REQ, where V is EMF. And this is equal to V over R1 plus V over R2. V is EMF. The EMFs cancel, and this is a derivation of the formula for adding resistors in parallel. Now I'm going to discuss power in circuits. Energy is given to the charged particle by the electric field doing work on it. Here's a resistor. The electric field within this resistor is doing work on the charged particles inside the resistor. The charged particles are the small little orange dots. Energy is transferred from the charged particles to the resistive pegs. If there were no atomic nuclei here, and there was just an electric field, these charged particles would be speeding up and gaining kinetic energy in the form of 1/2 mv squared. However, the current remains the same, and the speed of these charged particles is not changing. And the reason is because there's work being done on these particles by the field, but then they're running into these atomic nuclei or resistive pegs, which is causing them to slow down. Energy is being transferred from the charged particles to the nuclei. Power is energy per time, and the units of power are watts. Power is dissipated in the circuit, and the formula for power are provided on the slide. P equals IV, P equals I times V, but V equals IR, so you can write P is equal to I squared R. I is current, V is voltage. It's the current through the resistor and the voltage across the resistor. I is current, R is the resistance value. P is equal to I squared R, I is equal to V over R, so you can also write power as V squared over R. This is power which is given to the resistor. There's energy per unit time which is being provided by the battery, and that energy is going into the resistor to do work and cause some sort of outcome that the person who designed the electronics is looking for. On the upcoming presentation, I will address numerous common and relevant problems that encompass the content discussed in this presentation. In this presentation, my focus was on the fundamental concepts of DC circuits and the underlying reasons behind the flow of current. Understanding circuits requires a clear physical picture which greatly facilitates comprehension. However, while grasping the concepts and visualizing the physical picture is crucial, it's equally, or more important, to apply your knowledge to solving many problems. Please see my next presentation on DC circuit example problems.
AcePhysics.org